The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI Web Sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Ed Mclean has been involved in construction aggregates since '74. He's owned and operated his own production, pumping, and concrete construction firm. He's involved in bridge construction repair and overlay since '82. He's presently Director of Engineering Sales, Central USA for CTS Cement Manufacturing. Ed Mclean.
Now we've got to figure out how to use this little thing right here, right?
The one on the right.
Gotcha, okay. I first want to say this is somewhat of a tribute to Ed Rubin. He was not able to join us at ACI this year due to health reasons, and I'm honored to actually be able to be the presenter of this program. Ed is known for his development of ASTM C845 cements as well as the ASTM C878 NATO 6 test protocol restrained expansion test. As it was indicated earlier by Ed Rice, actually. And when he wrote his article back in 2006 in regards to crack-free decks, I actually assisted him in gathering some of the information, some of the documentation, a little bit of the bridge survey information that was out there, and I found out his passion for this technology. So it is a great pleasure for me to be here today. Something that we as engineers in our community we haven't realized is that what is allowing us to get the benefits from this technology, this shrinkage-compensating cement technology. And so in regards to this, there's also a lot of questions in what we're trying to deal with. Now, back to my original statement, what do we not know? Well, I believe that we just learned a lot from the speaker before me here in regards to what the actual shrinkage-compensating concrete can do in its expansion, how we restrain for it, and a number of other characteristics that are in regards to the shrinkage-compensating cement. But in this particular presentation, I'm going to talk about what are we trying to deal with, and that's cracks. And it's interesting that in 2010 a study came out, and it was about cracks, and that, well, the cracks lead to paths for moisture to get to the reinforcing steel, and the reinforcing steel corrodes. Well, in essence, we already knew this, but this was what happened in 2010. But what happens between the cracks, okay? What happens between the cracks? We have to have a concrete there between the cracks that's actually sufficient, okay, to handle the chloride attacks and other things. So we're looking at porosity and permeability as well. And right now we have that technology. We've had that technology since the 1960s. This is a picture that was actually taken this year on a bridge survey that actually Dr. Ramsayer and I were present on up in Michigan and Ohio. And this happens to be a deck that was placed in 1994. It's a Portland cement concrete deck. And this deck is very typical. If you look at the cracks in there, you can see these cracks are about every 4 feet. And again, very typical type of cracking. Now, in the 1980s, we decided we had to try to address these cracks, okay? And 2 gentlemen came out by the names of with an article by the names of Gruner and Paul Bruner and Alan Payne. And they wrote an article saying that we've got to address these cracks. This is an issue that we have to deal with because it's going to deteriorate our bridges. And we also decided that we were going to look at the permeability. In late 1989, we had a gentleman by the name of Ken Bright that came up with a rapid chloride permeability test. And this allowed us to see how dense that concrete really is. So we also, at that point in time, we started looking at the porosity of our Portland cement concretes. In addition to these cracks that we saw on the bottom side, they tend to want to migrate. If we have enough restraint in Portland cement concrete, they'll end up migrating into the safety barrier walls. If we start looking at these cracks as compared to the Portland cement concrete to the type K concrete, we're basically looking at the transverse crack density, okay, or the crack density itself being much greater than the cracks that are associated with the shrinkage compensating concrete. These two decks here were actually placed at the same time, 20 years old, and one was placed with the Portland cement concrete, and at the same time the shrinkage compensating concrete was placed. So we can see here that what the results were, and this is carried forward with all the studies. So since the 1960s, the use of concrete, the elevated decks, the conventional reinforced concrete and post-tension structural decks, we've started seeing the use of the shrinkage compensating concrete get used more and more. ASTM C845 defines cements in the groups of K, L, and M. And interestingly enough, none of these are really proprietary at this point in time. We also know that the SRAs that are out there, the admixtures, really basically delay shrinkage. And the G additive, we're not really sure where it falls in. But interestingly enough, there's not much history in regards to the latter two that we're speaking of here. The technology that we're looking at the Pennsylvania Turnpike in 1980. They did a number of bridges. Somewhere around the neighborhood of 30 bridges were placed in the state of Pennsylvania. In the 1970s, this is in New York State. If you start looking at what the history is here, we start adding up these number of bridges, and you can start seeing that the numbers were back there in that age time, and we go look at those bridges today, and we find that these bridges are still performing quite well, and in many cases have not had any type of repairs to the surfaces. So the ASTM C845, we've got 600 bridges and counting. We've actually lost count of the number of bridges that are out there, and the performance is excellent. This confirms Ed Rubin's paper in regards to crack-free concrete. The surface condition, we're actually seeing the tines being maintained throughout these decks. And little noticeable wearing on those surfaces. They're in pristine condition. And we're not showing fault from the de-icing chemical attack, which leads us to want to ask the question, is the porosity of this concrete lower than that of the concrete of type 1 or type 2 Portland cement? And going back now to some of the study that was conducted this year in Ohio, this is a picture of the Ohio Turnpike Bridge. This bridge is only a few years old, but you can see that it's in pristine. There's no cracks in this deck. This one here was placed in 1994, and you can also see there's no cracks up here. Now, this particular picture here is a concrete girder system, okay, whereas a lot of the bridges in that same region are steel girders. This is just a little closer up picture of the same type structure, 18 years, an I-69 near Lansing, and we can see no cracks in the concrete. This is an interesting thing. This was done in Brown County, Ohio, and I want to get the date here on this, if you just mind for just a second here. This was Brown County in 1985, and this bridge was two bridges side by side. This was placed with Portland cement concrete. This one was placed with the shrinkage compensating cement concrete. Same time frame, same month and everything. Interestingly enough is that they wanted to see this activity. They wanted to see the reduction in cracks, but actually it was rapid chloride permeability they were looking at. And the test results on the rapid chloride permeability, the Portland cement concrete on the first picture you saw had a coulomb of 9,015 coulombs at 28 days. The shrinkage compensating concrete had 2,786. Quite a lower amount of resistivity there in regards to the difference of the concretes. Now, the question comes up, do we want to get a lower permeability? Well, yes, possibly, but at this time, this is 1985, we were just now getting into the idea of what we were looking for reduced porosity and reduced permeability. Something else that comes into play is the type of structures here when it comes to the integral abutments. As you can see here, this was a steel girder. It's cast into the concrete abutment. Here's the concrete version cast into the concrete abutment. And what we're finding is that the concrete deck that's placed on top of here, there is so much stress from the shrinkage that's taking place on the deck that we're getting a lot of cracking, and it's basically because the ends are restrained and the cracks start showing up throughout the entire deck. This is really evident when you start looking at voided decks or box decks, where they actually can radiate up at an angle from the abutment into the deck through the, just basically very well spaced, every 4 to 6 feet. This is just another couple of pictures of the abutments here, the integral abutment. And you can see there's no cracks up between the concrete girders. This is actually pictures of a bridge that was cast in 1996 in Michigan. This is the non-integral abutment. This is allowing for some movement in the deck itself. Now, this is on this particular job. I don't show the other end, but the other end was actually integral abutment. This end was non-integral abutment. So there was allowable for movement. There was center column pier cap configuration between the lanes of the interstate. This was actually over the interstate and on there in Michigan. And you can basically, they are allowing for movement of some type in this structure. When we get to the surface conditions of the concrete, we now start looking at 15 years of this concrete. What does it look like? If you take a Portland cement concrete deck at 15 years, you're starting to lose your tines. You're starting to see wheel ruts. Well, what's taking place here is, according to ACI 223, and also the knowledge that we have on shrinkage-compensating concrete, that water grab is contained within that cement, used up in hydration, so basically we don't get any bleed water. And because we don't get any bleed water, the water-cement ratio on the surface is the same as what the rest of the concrete is. So we don't have a reduced strength of concrete. So the abrasion resistance is quite high. And actually they claim it's 30 to 40% higher. And actually in Michigan and Ohio, most of the bridges that were cast back in the 80s and 90s still have 70% of their tines left. There's no wheel tracks, no scaling. And basically they're looking at a 35-year deck, which we'll talk about here in a minute. Ohio Turnpike Overpass, this one right here is basically one that we saw some cracks in the head wall, but they had not migrated into any of the deck area or the structure itself. M6 US 130 in Grand Rapids. There was a major project that took place there all at one time period. There was 20 miles of new freeway. There are 57 bridge decks constructed with shrinkage-compensating concrete, and 40 bridge decks completed alone in 2005. This was basically done by one ready-mix producer. At that point in time, his biggest problem was availability. We don't have that issue anymore because of the availability of the shrinkage-compensating cements here in the United States. But that was his biggest problem. Producing a good concrete was not a problem. The Michigan DOT was very much involved in this program, really studied this, and we actually came up with some of the original specifications that are now pretty much generic and prescriptive of nature that are being used throughout a number of the states. In Michigan M6 bridges, traditional design, steel and such equipment. And speaking of the mixed designs themselves, we can see here that we're not looking at a tremendous amount of cement content. It varies a little bit from state to state. Has a lot to do with the aggregates that we're dealing with, and also the Portland cements. The reaction of the Portland cement with the component, with the concentrate. Excuse me. Fly ash has been used considerably. I've had a lot of experience personally with the use of fly ash and even some slag, and we can use that successfully, especially in summertime applications where fly ash is a good finishing aid or retardation type of thing in the set times. Air and mid-range water reducers work phenomenally well, and high-range water reducers can be used upon need. And also in some cases where states are a little subject to the use of the retarders, they can be used, but again, that's based on what the state's applications are and their permissions. Some of the other things that we're looking at here is that it does require a 7-day wet cure, okay? But in most states, that's what the states are requiring now on all their bridge deck overlays, or bridge deck construction. So we're basically looking at the same apples to apples as far as the curing. Can these jobs get quite elaborate? They sure can. This happens to be the Lodge project that was in 2009. What's behind me here is the Ambassador Bridge over to Windsor. There's multiple levels of interstate here intertwining with each other, so it's very complicated to get to this project, let alone the place and finish equipment having to get up on top. And in this situation here, we were using multiple pumps actually. So the concrete was coming to the job. We had multiple pumps. It was no issue. Pumped quite well. We actually were placing this concrete in some areas on this project in a skew and in an incline, in a horizontal incline type of an application. So we were working with flat concrete. We were working with different elements here. So some of the myths that are out there that shrinkage compensating concrete requires special equipment, such as the pumps or the place and finish equipment. No, it basically works just the same as any other concrete that you've used out there as far as the Portland cement concretes are concerned. Interestingly enough, we're using a higher water cement ratio. The shrinkage compensating cement requires that. And that water is used up, but we're actually able to deliver to a job site a good 5 or 6 inch slump concrete, not a 2 inch slump concrete, not a 1 inch slump concrete, which is very nice and very favorable by the workers themselves. It can use the traditional design and reinforcing. We're not changing up on these structures at all. These bridge structures, we're not changing anything. We can place during the daytime or at night. Now, in the summertime, it is favorable to place shrinkage compensating concrete at night, but it's also favorable to do that with Portland cement concrete. And we use the same type of practices for cold weather and hot weather. Again, back to some of the equipment. This is a standard bridge deck machine. It's self-propelled, can move backward and forward, and works quite well. And what's really nice is that these shrinkage compensating cements actually have a finer blade, and we end up with a little creamier texture to the concrete. So the machines actually move across and the closure is very nice. Just a quick picture, this right here was basically 7 days after the placement of this one section. Again, this ASTM C845 type K shrinkage compensating cement in Ohio has been used since 1968. There's been a number of articles written out there, numerous articles, found some that were written back as early as 1991, and in Concrete International, Concrete Construction. We have established the fact that this concrete does have a lower permeability than traditional Portland cement concrete. And it has been used in well over 600 bridges. And again, we've lost count. Basically in Ohio in 1968, the first project there was US Route 33 in Marysville. And in 1964 on I-675 in Dayton, all the bridge structures used black bar. They did not use green bar in this. And those structures today, we went and looked at those, and there is no spalling and no corrosion problems in regards to those decks, and we couldn't find cracks in these decks. Now, there are some areas that have actually had an epoxy overlay, but that's been for some other reasons, but these decks are in pristine condition. What's really interesting here is that I attended a bridge conference back in 2008, and I don't like to read off of slides, but I'm going to read this. High performance bridge deck, use of ASTM C845 type K shrinkage compensating cement with lightweight aggregate for optimized internal curing, excellent durability, and performance benefits. These are the authors that are listed here. There was 15,000 yards of concrete at 120 pounds per cubic foot unit weight, okay? It was a 715-pound cement mix design. Basically of which 100 pounds was the component. This is on the lakefront, and they call this HPC. I believe the reason why I wanted to show this HPC is because we've overused this terminology, but it is a high-performance concrete, okay? It does provide for performance that you do not get with Portland cement concrete. Elongated sections. One of the things that we run into with shrinkage compensating concrete on bridge decks is that they're narrow and long. And we're not finding problems with that. We're not getting cracking in these decks, and it's a lot to do with the amount of restraint. If you think about it, you've got 2 mats of steel. It's a structural element. And so we're taking advantage of that in these structures. But this is not unusual. I believe this overall deck right here was right at 1,800 feet. It was poured all in one mooring, okay? They had 2 ready-mix plants batching for this. And then we have some of the smaller ones. Here you can see a traditional construction site. This is actually a steel girder bridge. This was this year in Elyria. Green bar going in. And they're going to tie the safety barrier walls, both on the sides and the center, to this deck. And they're going to basically, it's rigid. Something else that we run into with a lot, and people would say, how do you deal with skews? Well, with the shrinkage compensating concrete, we're not seeing cracking in the skews, which is very, very common with Portland cement concrete. And this is a big thing. I mean, this is one of the places that you go to as an engineer to inspect a bridge deck. This is one of the first places you would go to look and see what type of cracking you're having and what's developing in that structure. We get to the Ohio Turnpike, and the Ohio Turnpike has been very satisfied with the results of the concrete for a number of years. It addresses many things. Safety and ride characteristics, they have no problems. They love it, whether it's on mainline interstate or if it's on the overpasses. And here's a quote from the chief engineer there. "We don't even think about cracks, crack maintenance, or spalls on our concrete or our shrinkage compensating concrete. We're expecting 35-year life on the decks and their wearing surfaces." Okay? What he's related to is that he's not going to go out there and have to make repairs. Now, what they did is they did a study, and this is just part of the study. This happens to be a study that was conducted starting in 1983. It concluded in 1984 on this part of it, okay? And that's very confusing data that's sitting here. I'm going to throw it in a graph form in a second. But I wanted to show some of the numbers here as far as the number of bridges. If you look over here, over here on the far right on this, or underneath that, it says 50% Portland cement concrete. There were 6 bridges that were constructed. You see that? And then in 84, there was 67. Those 2 years was Portland cement concrete. From there down, this was all shrinkage compensating decks. You can see 45, let's see, you've got 38, 45, 59, and 74 bridges. So there's quite a few bridges. Looking at this graphically, if you look at 1983 and 1984, these were when they were doing just the Portland cement study, you can see the various different crack characteristics. They rated them in 4 ways: none, minor, moderate, and severe. And as you can see that in 1983, approximately 50% of the bridges that were done, there was only 6 of them, by the way, 50% of them had no cracking in that at this point in time in the study. However, it looks like we had about 18% that had moderate. There was no severe. In 1984, for some reason, that same mixed design concept with Portland cement concrete, they started seeing a lot of severe cracking, as you can see in this diagram. When they went to the shrinkage compensating concrete, 87, 88, 89 time period, you can see that there is no cracking in over 95%. In fact, as in 1989, the bridge decks there, 100% of them had no cracking. When asked the question, how does this affect the maintenance costs to these people at the Ohio Turnpike? The answer was quite simple. Very low cost to maintain the actual shrinkage compensating concrete decks, no delamination, spalls, or steel corrosion. Okay, they're not spending money on their maintenance there on those decks. Okay, so that's saving them a considerable amount of money. It's paying for itself over time. Where has this taken us to in other states? Now, I've shown pictures of a number of the states, such as Ohio, Michigan, Pennsylvania. We've got bridges in Virginia, West Virginia, New York, New Jersey. So we could be sitting up here all day long with a lot of different pictures, but where are we going with this? Are other states picking up on this? Yes. Missouri Department of Transportation, we did our first deck this year. It was quite a unique type of a deck construction, and it was placed in 2 different placements. We used the traditional Michigan and Ohio specifications for this. We got adequate expansion in all of our testing with the 878 testing protocol. Everyone was satisfied, and they placed this concrete. But something very unique happened here. This was not the traditional mix, though, that we used. We actually increased the cement content because we were looking for a 3-day turnaround. We needed 4,000 PSI in 3 days. Now, this was not rapid set, as was asked earlier. This was actually the shrinkage compensating cement component, as well as Portland cement, and we just increased the amounts. We did a 3-day wet cure, and they basically put a curing compound on it after that 3 days and opened it to traffic. We had our 4,000 PSI. It was very creamy, very easy to place. We were basically averaging 6-inch slump. We were running at around 5% error entrainment on the mix design. This was placed at nighttime. A very heavy trafficked area. The name of the road in St. Louis's page, it's Highway 100. Very heavy traffic area on the west side of St. Louis. Now, in Illinois, we did a bridge deck. And some people say it's the first time we've done it in Illinois. No, this is not. We actually did several bridges back in the 90s that, upon survey in 2010, were found to have no cracks and in pristine condition. However, the state of Illinois decided they wanted to revisit this with a redesign, so to speak, and they did not accept the mixed designs or the specifications from Ohio and Michigan, and set out to come up with some of their own new specifications. And I can tell you that by using their mixed design program, we ended up with a good concrete, but we did not get the strength gains, and we did not get the expansions that I would like to have seen. And so why we changed that, I'm not really sure, but this is something that we're still exploring. But this deck right here has no cracks in it. And there's a bridge that's just a quarter of a mile to the west, or to the east of this one right here, that was Portland cement concrete that was placed the week before, and it's got a crack every 4 foot. Okay? Same type of design that you see in this right here. Where are we going with this? Well, in Knoxville, Tennessee, several years ago, we did an overlay on a viaduct that was a very, very major and very high-profile viaduct that takes you down to what they call the Museum District. And this was done over a bridge that was actually built probably around 75 years ago. The concrete that was put in here was a shrinkage-compensating standard mix design. Again, we were using the standard mixes that we would use like in Ohio and Michigan, about 100 pounds of components, 600 pounds of Portland cement. They placed this with a concrete pump. It was 4 inches thick in its thickness, and it's provided a very adequate wearing surface. One step further than that, though, Mike Sprinkle with the Virginia Department of Transportation has added latex. And we'd be using some other polymers as well right now with the technologies that are out there to reduce that permeability, which was earlier in the program I was talking about. That's the one thing we haven't really gotten to. And he was able to get a shrinkage-compensating concrete with less than 1,000 coulombs in 28 days. Something else with shrinkage-compensating cement, it's produced differently than Portland cement because it doesn't take as much energy. There's a few other things that are factors in producing the shrinkage-compensating cement, but there's lead points that are involved here. And believe it or not, I'm starting to see where the DOTs are starting to look at that at their structures, getting lead points. They're going green on us. The other thing is that there's several international cement companies that are actually marketing shrinkage-compensating concrete or cement in the United States. We sell primarily to the ready-mix producers because this is something we'd like to control from a ready-mix production, especially being in mostly exterior applications. Some of the silos have been, some of the silos are now owned by some of the flatwork contractors, and I've actually seen one of these flatwork contractors get into some bridge construction. It incorporates traditional concrete mixes, materials, aggregates, and such, and it's very workable. So in conclusion, I want to thank you. This was really fun for doing this again for Ed Rubin, and look forward to any questions.
What about parking garages?
It's any elevated deck. Earlier presentation commented on post-tensioning. We see a lot of post-tension parking garages. Yes, it's the perfect application. I'll tell you what's really nice is that if you get into a large parking structure where you're looking at closure strips in regards to using Portland cement concrete, we can get away from the closure strips with the shrinkage-compensating concrete. If it's a cast in place, it's no different than a bridge deck. You have the same elements there. So actually in those situations, I have one parking garage right now in St. Louis that's scheduled to be built in the next 2 years. Money, it's a money issue. But they actually, the engineers actually reduced the floor thickness from 9 inches to 8 inches. So his floor thicknesses have come down with the shrinkage compensating concrete. Yes, sir.
Yeah, it looked like most of the projects you were showing are using a water cure.
Yes.
Is it possible to use a fluid applied curing method?
I've experienced the use of a fluid applied twice now. I'm going to use the brand name. It's Sinec. Okay, it was the product that was used. It was used in Missouri on the bridge that we did this year at 3 days. They also used it on a bridge up in Michigan that had a 5-day closure limit. So they used it at 5 days. So we went 5 days with wet cure, then we put the product on there for membrane. I have not seen any of these bridges that were not water cured, though, to answer your question.
You mentioned dollars. How much does it cost?
And again, you're basically in percentage of cost of the concrete, okay? Percentage cost of the concrete. You're adding, let's see, well, it depends on what the price of concrete is, but let's say you're adding about 10% to the cost of the concrete. But if you look at what Ohio Turnpike said, it really depends on the size of the project. Ohio Turnpike has seen, from the ready-mix producers in Ohio, we've seen an increase in the price of concrete anywhere from $30 to $35 a yard. Okay? That would be for their use of their silo and their inconvenience and everything else. But what the state, or what the Ohio Turnpike, the DOT there is stating is that they're not having the maintenance costs. So they're actually saving a considerable amount. So they're actually looking at not only the in-place cost, and they look at the total in-place cost, but they're also looking at that long-term cost. Yes, sir.
I saw a number of, I think, 715 for your cement factor. Are you then adding shrinkage, this type K on top of that, or replacing some of that? And are you getting very high paste contents, but yet it's not seeing cracking in bridge work?
Okay. The traditional mixes have been basically 600 pounds of Portland and 100 pounds of component for bridge decks. Okay, now this is not floors, this is not containment, this is bridge decks. The cement paste factor is not an issue at this point in time. We're not having any, we're not seeing shrinkage cracks, okay? We're not getting shrinkage. In fact, as all the 878 tests, we're getting somewhere in the neighborhood of 0.03 to 0.06 on our expansion. So that's an excellent expansion in regards to these mixes. Yes, sir.
The reduction in permeability, is that caused because of the concrete in compression, or is it some special chemical reaction in the concrete that caused the reduction in permeability?
This is something that needs to be looked into further. In fact, is Plain and Gunner and Mclean, they mentioned this earlier on, that this needed back in '93. This needs to be looked at with more detail, and no one really has. To answer your question, I honestly think it has a lot to do with the blend of the shrinkage compensating cement. You're putting 15 to 17% into that mix design. And it has a higher density, okay? And you're also using some chemicals in there. You're using water reducers. But what you end up with is a denser concrete, okay? What it comes down to is a denser concrete. We know denser concretes are going to be less permeable, less porosity. So we need to study that. What can we do to improve upon that? Well, I'll tell you, we have a lot of new polymers, not the old latexes that are 40, 45 years old. We got these new polymers out there today that do a remarkable job of getting into the solution very quickly. They address things such as porosity. They also look at, some of them even could be combined with corrosion inhibitors, which is a big additive that we need to be looking at. So we've got a lot of opportunity here, but no, this hasn't been studied well enough. Yes, sir.
Did the Ohio bridges use your additives in your bridge design mix?
Our additives?
No, you were talking here about additives to decrease porosity.
Oh, no. All the Ohio bridges from day one, they have not used anything other than the shrinkage compensating cement, Portland cement, stone, sand, and water. They have used water reducers and air entrainment, to answer your question. Yes.
So it's not needed?
It's not needed. We're not seeing, if you look at it this way, if we have a concrete, I showed you the wearing surface, 15, 20-year-old wearing surface here. If we're not seeing a deterioration of the wearing surface, that tells you a lot in regards to the resistance, the porosity. I mean, if you're not seeing that breaking down, and we all know what happens there. In Ohio, they put a lot of salts and a lot of chemicals on there. So we're not seeing that. And if we don't have the cracks, now you don't have the migration of the water to the reinforcing. So the answer, Dr. Ramsayer's question, no, they're not using it, but if that's something we need to address at some point in time, there are some avenues to go, and it's not that expensive. We're not talking that big great of an expense to do that. Thank you very much.